Hello everyone, welcome to my YouTube channel. In this video, I'll be explaining about IR spectrum, the principle that is involved in the IR spectroscopy, and also how to solve the IR spectrum and certain peaks, how to select this certain peaks and identify them, and to identify the functional groups present in the molecule on the basis of IR spectrum. So first coming on to, as we all know, IR spectroscopy involves when the molecules absorb in the infrared radiation. So here we can just see here in the electromagnetic spectrum, when the molecules absorb radiation in the infrared region, so then it undergoes vibrations. So we know that in UV visible spectroscopy, when the molecules absorb in the UV visible region, then they undergo electronic transitions. Different types of transitions are also observed, like sigma to sigma star, pi to pi star, etc. But in case of IR spectroscopy, that is, when the molecules absorb radiation in the infrared region, then they undergo vibrational movements. So again in the IR region, we have three different regions, that is, far infrared region, mid-infrared region, and near-infrared region. So the molecules can absorb radiation from any of these regions in order to undergo vibrational movements. So here, mainly this is a typical example or a typical representation of an IR spectrum. So we usually express this the vibrations, that is the vibrations that are taking place in the molecules, in terms of wave numbers. So here we can see in the x-axis we plot wave numbers, but whereas in case of UV visible spectroscopy we usually measure the wavelengths, that is the lambda max values. But here in the IR spectroscopy we express this in terms of wave numbers. So wave number is nothing but the reciprocal of this wavelength. So we express it in the form of centimeter inverse. So now the principle that is involved in IR spectroscopy. As I told you all before itself, the IR spectroscopy involves the vibration of the molecules. Again in vibration, there can be two different types, that is stretching of the bonds and bending of the bonds. So here, let us just consider a simple molecule that is represented by AB. So AB is nothing but two different atoms which are connected to each other by one single bond. So here, suppose there is only one bond between the two different atoms, then what are the changes that are occurring when this molecule absorbs radiation in the IR region? So the only vibration that is possible when a diatomic molecule absorbs radiation in the infrared region is bond stretching. So during bond stretching, what happens is the bond length increases and decreases continuously. So you can just see here, this is just an animation to show how the bond stretching occurs. So here, the two atoms will move far from each other and come closer to each other. In the meanwhile, the bond length increases and decreases continuously. This is the case only when we are considering a diatomic molecule, that is, when only two atoms make up one particular molecule. But suppose we are considering the molecules with more than two atoms, then there will be one more type of vibration which is called as bending vibration. So during bending vibration, there is change in the bond angle. So we'll be just in the further slides, I'll be explaining the main difference between the stretching vibration and the bending vibration. And again, in the stretching and bending vibrations, there are subtypes. So what are these different types of stretching and bending vibrations, which all together make up the vibrational movements of the molecules? So coming on to the stretching modes of vibrations. So there are two types of stretching that can take place in a particular molecule when they absorb radiation in the infrared region. So first type of stretching is symmetric stretching. You can just check here how it occurs. So here, the two atoms move away from the central atom and come closer to the central atom in the same time. You can just see here. The two atoms are moving far from the central atom and coming close towards it at the same time. That is, they are making it together. Okay, so such type of stretching vibration is called as symmetric stretching. So it can be defined as the movement of atoms with respect to this particular atom in the same direction. So you can just see both the atoms are moving in the same direction with respect to this central atom. Next, coming on to antisymmetric stretching, or we can also call it as asymmetric stretching. So symmetric is both the atoms moving in the same direction. So what will be antisymmetric? That is, one atom is moving in one direction, whereas the other atom is moving in the opposite direction. So we can just check this out. So antisymmetric stretching or asymmetric stretching is the one in which one atom moves in one direction and the other atom stretches in the opposite direction. So this is asymmetric stretching. So in stretching, we have two types. Again, in terms of bending modes of vibration, there are four types of bending vibrations. So first type of bending vibration is rocking vibration. So you can just check this, how this bending of the bonds take place. So here, the direction of movement of the molecules is towards the same side. That is, bending occurs towards the same side. And one more thing what we have to observe is the bending occurs in the same plane as that of the central atom. Okay, so bending occurs in the same plane as well as it is occurring in the same direction. The two atoms are bending in the same direction. Next, coming on to wagging vibration. So here, again, the bending is occurring in the same direction, that is bending of the two atoms with respect to the central atom is occurring in the same direction, but they are not in the same plane with respect to the central atom. They are bending out of the plane of the central atom. So this type of vibration is referred to as wagging vibration. Next, coming on to twisting vibration. So here you can just observe the two atoms are bending in opposite direction with respect to each other. Okay, so when one atom moves forward, the other atom moves backwards. So here the movement takes place in opposite direction to each other and the atoms are moving out of the plane with respect to the central atom. So this type of vibration is called as twisting vibration. Next, coming on to the last type of vibration, which is called as scissoring vibration. So this vibration is similar to that of the normal scissors which we use. Here, the two atoms move far from each other and come closer to each other, but they are occurring in the same plane. So the movement of atoms is in opposite direction, but they are occurring in the same plane. So this is one type of vibration which is called as scissoring vibration. So we have seen four different types of bending vibrations where there is change in bond angle with respect to vibration. Next, coming on to the two different regions in the IR spectrum. So the two main regions which we have to see in the IR spectrum is the functional group region and the fingerprint region. So the functional group region, as the name suggests, it will help us in identifying what are the functional groups present in the molecule. Same way, the fingerprint region, as the name suggests, it is very specific to that particular molecule. Similar to our fingerprints, even our fingerprints are not similar with each other. That is, each person has his unique fingerprint. Same way, each compound has its own fingerprint, or in other words, the fingerprint region of a particular compound in the IR spectrum is very specific, or it is characteristic feature of that particular compound. So this functional group region mainly is in this range, that is 4000 to 1400 centimeter inverse, whereas the fingerprint region ranges from 1400 to 600 centimeter inverse. So let us just see how we can identify the different functional groups in the functional group region. So as the name suggests, functional group region, so here we identify the different functional groups of the molecule. So if we see any peaks here at this range of 2900 to 3000, then we can easily identify that there is a CH stretch in the molecule. Same way, a very characteristic peak which is observed here is the peak that will be observed at around 1700 centimeter inverse. So whenever there is a carbonyl group, that is C double bond O group in the molecule, then we can say that here in the IR spectrum of such molecules, we can see a strong peak at 1700 centimeter inverse. So this is an example, again, one more example of an IR spectrum. This is the IR spectrum of ethanol. Here, the very characteristic peak is the one which is observed at 3300 centimeter inverse. So if you see a broad peak, okay, at a broad peak at around 3300, then we can say that the molecule has OH group. That is, the OH stretching will give a broad peak at 3300 centimeter inverse. And at around 1000 to 1300 centimeter inverse, if we see a strong peak, that indicates there is a CO stretching in the molecule. That is, C single bond O stretching in the molecule. So just by comparing these two spectra, it is very clear that it indicates two different types of molecules. The previous spectra, it indicates butanone, which indicates it is a ketone. So ketone should have a C double bond O group, which indicates there should be a strong peak at 1700. Whereas this strong peak at 1700 is not observed here. That means here there is no C double bond O group. So here in ethanol, the characteristic functional group is OH group because it is an alcohol. So we can observe this peak, the broad peak, which indicates the presence of OH. Whereas this broad peak is not observed in the spectrum of butanone, which indicates here there is no OH group. So it is very clear that just by seeing the functional group region of the IR spectrum, we can identify the main functional groups that are present in the molecule. So next, coming on to what is the fingerprint region. So as I've told before itself, fingerprint is very specific to that particular spectrum. So it is a characteristic of that particular compound. So each spectra will have different types of peaks in its fingerprint region. So these two spectra mainly indicates the types of alcohols. This is also an alcohol with the functional group OH, and here also the functional group is OH. So we can see these broad peaks at around 3300. But if you observe the fingerprint region, it is completely different from each other. So although the functional groups may be same for the two different molecules, it does not indicate that the fingerprint region peaks will also be similar. The fingerprint region of the two molecules will be completely different from each other. So we can say that the fingerprint region is a characteristic of that particular compound. Although the functional groups may be same within the different molecules, the fingerprint region will completely be different from each other. So in this video, I have explained about the principle of IR spectroscopy and about the different types of regions that we observe in the IR spectrum. In my next video, I'll be explaining about the characteristic peaks that are observed in the IR spectrum and how to identify the peaks if a particular spectrum is given to you, and how to assign the different peaks to the functional groups in that particular molecule. Thank you for watching the video.